Hi everyone, and welcome to a new video about controller realization, and this is our example number 4. In this example I would like to discuss the realization of a lead controller. So we will move on via the discussion towards a circuit that can realize our given controller transfer function for specifically now the lead controller. Of course, we work everything out in our calculations step by step and also verify these in our SPICE simulations. So let's look at an example. We would like to design a physical electronic circuit for this given transfer function, which is a transfer function of a lead controller. Now, before we move on and dive into the calculations and the discussion in the simulations, what is a lead controller? Lead controller is a controller that has a pole and a zero, and the pole is farther away than the zero measured from the vertical axis in the complex plane. When you look at this transfer function, you can see that actually clearly the 0 is at -2, which is then given by the denominator as equal to 0, and in the numerator I mean, and the denominator equal to 0 will give you a pole at -25. So -25 is far away than the -2, so this is definitely a lead control. If it is a reverse, for example, this is 25 and this is 2, so the pole is closer than the 0, then we have a lag control, and we will discuss this in another video later. Okay, so let's look at the solutions and then see how we can make an analog electronic realization for this transfer function specifically. Now we start with the transfer function of the circuit, and this circuit is a possible option or candidate for realization of this transfer function. There are many others, so this is just a simple option for this specific transfer function. So we can know, and we already know from the circuit analysis, that we can use the voltage divider rule to get the transfer from the input to the output. The input and the output are already given in the capital letters, so that means we already work in the Laplace domain or the S domain. So we can say the VO over the VI, and I call this transfer function of the circuit H, and the transfer function of the lead controller is already given as G lead. So what we do is then we look at the VO over VI. For that I can say this is the R2 over the impedance here plus the R2, but the impedance here is not determined yet, so let's give it a name, which is the ZA, and ZA is actually the parallel combination of the R1 and the reactance of this capacitor C. That is X of C. X of C is given in the Laplace domain as 1 over SC. So when we move on and use the parallel formula for the parallel combination of two components formula, and then you get this expression. So you multiply the impedances or the reactances of the two components, the resistor and the reactance, divided by the summation of these two, and you can simplify this to get this expression for the ZA. Now we know the ZA, now we can say this is the impedance, so the VI is then equal to the complete impedance ZA in this R2 times the current flowing in it, or use of course the voltage divider rule as said before. So we can say this R2 over R2 plus ZA. So we have directly our voltage gain or the expression for the transfer. So we have now here the R2 plus the R2 plus the ZA here, which is this expression. So we can now substitute that. Now if I do that, I will have here this expression. We can simplify this expression further by get rid of this fraction, because in order to get rid of this fraction, I need to multiply the numerator and the denominator by R1CS plus 1. And that's the next step. So you can see that. So you will leave only R1 here. This R2 will be multiplied by that coefficient, and this R2 also the same thing. Now we can bring the R1 times C out of the parentheses. Why? Because it's also here, because it is S plus 2 and S plus 25. So the S is isolated. So in order to compare that easily and directly with that given transfer function of the lead controller, we will do that. So that will be then the following step. And that means if I take this out, I also need to do 1 over the coefficient I take it out. That means 1 over R1C. That's the same here, and only unchanged parameter here is the R1 here as an expression. Now we see the following things. We can divide out actually this complete product, R1 times R2 times C, and also here. But when you do it here, you actually lose 1 R1. That means you get 1 over R2C. So you only leave in the denominator this. So S plus 1 over R1C. In the denominator you get S plus 1 over R1C plus 1 over R2C. I already give it a color, so as you see the red and the blue one. The red one is actually the 0 location, which is then a minus 1 over R1C. and the 0 is that, and the pole is given by this expression, which is then the minus of this quantity here, which is then given in parentheses. So if I look at these two transfer functions, I can now compare them easily. So let's do that. Compare the terms of the G lead and the transfer function of the circuit H. So we can see the following. 2 here must be this, so 1 over R1C. And the 25 here must be then 1 over R1C plus 1 over R2C. That's shown here. So we get here two equations, but we know already that we have three unknowns, so we need to select a value of one of the three. So we have three unknowns and two equations. So if I had three unknowns and three equations, I had a unique solution. In this case, I need to select one. Now, the most convenient one is to select the capacitor. In this case, I just select a convenient value, which is 1 microfarad. So that's the selection. That means now using this value, the R1 and R2 are now fixed by this choice. So then we get to follow from this expression. We get then R1 is equal to 1 over 2C. And since the C is now known, we can now write it down and then calculate it. It will be then 500 kilo ohms. Now, since the 1 over R1C is 2, that's also here. So in this expression, I can say, looking here, is 25 plus 2 plus 1 over R2C. That's actually shown here. Or 23 is equal to 1 over R2C. And since C is selected, that's known. So the R2 is the only unknown in this equation. So we can also calculate that using this. And you can now substitute the values. And you have now almost 43.5 kilo ohms. So a little bit smaller. And that is the result for the R2. Now we have the components, R1, R2, and the selected value of the C for this specific circuit. And this is the transfer function of the circuit. This is the lead controller transfer function. You can see the red one and also the blue one. You can compare that now much easily by next to each other. And this is a circuit I have drawn in Tina TI Spice. I will shortly give you the results in the frequency response also. And this is the circuit. You see the values for R1, R2, and also the capacitors C we have selected. So let's go to the simulation results, the frequency response, because there's a lot of information there. So let's begin with that one. You see here the low frequency gain. Let me start with that one. That means the following. What is the gain of this transfer function when the let's say the frequency is very small, or let's say exactly 0? Now, which is not possible because this is 100 microhertz, let's say 0.1 millihertz. So it is already very let's say low frequency. And I see minus 21.94 dB. And it's actually in scalar form 0.08. Why is this correct? Let me check that. Because low frequency gain in our transfer function can be determined by substituting in that transfer function for S is 0. If I do that, I will get 2 over 25. And 2 over 25 is then, using the calculation here, will give you minus, in dBs of course, using 20 log of that value, will give you minus 21.94 dB. So it is indeed correct. So this is again a proof that this is indeed correct. You can also check that 2 over 25 is also 0.08. That is also possible. That's the scalar value. So this is scalar value and this is the dB value. So we have now the verification of that one also. Let's also look at the high frequency gain, because what happens if the S approaches infinity? So very large values, 1 terahertz, a lot, very large values. Then the 2 and the 25 here actually do not matter anymore. So you get actually very large value divided by a very large value. So we approach actually 1. That is also 0 dB, and that's actually the proof here. So high frequency gain will approach 1. Of course, mathematicians will never do this infinite in the formula, but we just do that here. As an engineer, we don't have a problem with that. So we get here, and then 20 log of 1 is 0 dB. So again, a proof that the high frequency gain is indeed correct according to this transfer function. But by the way, this is the transfer function or the plot we have from our circuit. So this is indeed really giving the information from the transfer function. Of course, we have just checked two things, low frequency gain and the high frequency gain, but we also want to check the zero frequency and the pole frequency. So there are the next, let's say, checkpoints. Zero frequency here is given as 320.4 millihertz or 0.320 hertz approximately. If I convert that to the radians, you need to multiply then this by 2 pi f. You'll get 2.013 radians, and we had 2, so it's really close. So you can see that this is indeed very close to what we have given here as the lead controller. So the 0 is indeed 2, and we had 2.013. So very nice result. For the pole frequency, which must be 25. I see it is as a hertz. In frequency 2.95 for almost 4 hertz. But if I again multiply by the 2 pi, going from the hertz to radians per second, I get 24.84 radians per second. Also a little bit smaller, so you can see that this is smaller than 25. So it's still very close. So again, a nice result with in the simulations. You see actually the following also, the pole is a little bit larger than the zero. I mean, the zero is a little bit larger than the given zero in the transfer function. The pole is a bit smaller. So there's some, let's say, merging together. So the zero is a bit closer here and the pole is a bit closer to the left side. So it's kind of affecting each other in this combined effect. Let's also look at the phase plot of this diagram, Bode diagram, because you see the gain and the frequency here. That is actually discussed already in great detail. But there's also a phase plot as a function of the frequency. So the phase is going actually from very small, zero almost, and then going up, and it reaches some maximum value and then going down. So you see the maximum value here. It happens at the maximum phase contribution at approximately 1.126 hertz. So that's approximately 7.075 radians per second, and you get a maximum phase of 58.4 degrees. But how can we calculate this? This is also an important check that this transfer function is really giving that transfer function here. You see the following: the maximum phase contribution is that one, and maximum phase contribution can be calculated by the location of your pole of your lead controller and also the location of the zero of your lead controller, and product of that and the square root of that one, that's sort of the geometric mean. So you get the square root of 25 times 2, so square root of 50, which is 7.071 radians per second, which is very close to what we have here. So the maximum phase happens, that is the omega max, doesn't mean that the maximum frequency. It is the frequency where you have the maximum phase, which is at 7.071 radians per second. That's already verified by this calculation. Now, moving on, we would like to know also what the maximum phase contribution is. So this number I also want to verify, 58.4 degrees. Now, you get the maximum value of this gain here in the blue line using this formula. So you actually take the absolute value of the given transfer function. You substitute there the omega max, and then, of course, use the length of the numerator and denominator. This is from familiar business from complex numbers. Then you get the square root of 0.08 exactly, which is approximately 0.283. Now, this is the value here in the blue plot, but we of course need to know what this is in dBs, and if I calculate that, that will give me then some specific dBs, which is approximately minus 11. So you can go here. But this value here, what we just calculated, is equal to 1 over the square root of b, and that b is a parameter. And if you use this scalar value in here and do 1 over the square root of b, the b can be calculated, which will be then exactly 12.5, and you use this exact value of square root of 0.08. Now, the maximum phase can be calculated by using this formula. Again, I leave out the proof and the details. So arc sine of b minus 1 over b plus 1. We know the b, so we have this. And when you now calculate this, you get 58.4 degrees. So you see it is indeed correct according to the calculation we just shown you. So we see this circuit here will do the job, and it's also showing you that the zero frequency and the pole frequency are really close. And also, in addition, we have checked the high frequency and the low frequency gains, and also the maximum phase contribution by working out this analysis. Alright guys, this is for this lead controller design, realization of a lead controller transfer function, and using the passive components actually in this case, so you can also have an active lead controller. And I hope everything is clear for you. If you're not, please let me know in the comments. I will try to answer them as soon as possible. I will discuss in the next video about the lag and also the lag lead controller, and that will be uploaded as soon as possible on this channel. So stay tuned and see you next time. Take care.